Okay, so it's my pleasure to introduce Yandi from the University of Wisconsin-Madison and to tell us about marked length spectrum rigidity for surface amalgams.
Yeah, thank you so much, Michelle, for the introduction, and thanks for having me. So today I'm going to be talking about some marked length spectrum rigidity. So if you have any questions, feel free to interrupt. I think even if I'm like in the middle of a sentence, you can feel free to say something. So first I wanted to give an introduction and motivation to the problem. So I like to start with a really famous rigidity theorem called Mostow rigidity. And the original proof was in 1968, but since then there have been a lot of generalizations. So the original geometric statement says that if x1, g1 and x2, g2 are two closed negative hyperbolic manifolds where n is greater than or equal to 3, then if pi1 of x1 is isomorphic to pi1 of x2, we have that x1, g1 and x2, g2 are actually isometric. So this is a very strong version of rigidity because you have a topological condition implying a geometric condition. And there are some cases where it doesn't really hold. So for example, one thing to notice is that the dimension of the manifold has to be greater than or equal to 3. So you have that Mostow does not hold. First of all, for two-dimensional manifolds, so surfaces. And this is because of Techmuller theory. There's a whole Techmuller space worth of geodesics worth of metrics that you can put on a given surface with enough complexity. And also it doesn't hold once you introduce variable negative curvature. So M manifolds with variable negative curvature. Because like, again, hyperbolic means that the curvature is constant, the metric has constant -1 curvature. So once you allow for variable sectional curvature, then you no longer have a version of Mostow rigidity. So marked length spectrum rigidity, which I'm going to abbreviate as MLSR, addresses these two cases. So it's like a different form of rigidity that you might hope would work for these exceptions to Mostow rigidity. So that's kind of what I think is a good motivation for marked length spectrum rigidity. So now I'm going to define it. So first I need to define the marked length spectrum. So the marked length spectrum, which I'm going to abbreviate as MLS of a metric space, x comma g is a class function from pi1 of x to the positive reals. And it sends every homotopy class of curves to the infimum of lengths of curves in that homotopy class. So you take a homotopy class and you pick out a curve of the shortest length, and then the length of that curve is the marked length spectrum of the homotopy class. So this is a very general definition. There's no restrictions on the metric for the space that I'm looking at, But in today's setting, I'm going to be looking at negatively curved metrics. So in that case, there's actually a definition that I think is a bit simpler to work with. So if x comma g is cat minus 1, for example, or negatively curved in the case of, in the sense of Riemannian geometry, then actually each homotopy class of curves has a unique geodesic representative. So the marked length spectrum is a length assignment to every closed geodesic in your space. So this is a definition that I gave in my abstract. So yeah, I think it's a bit easier to work with. Yeah, so that's the marked length spectrum. And I think that now that I've defined the marked length spectrum, I can define marked length spectrum rigidity. So this is defined for a class of metric spaces. Is marked length spectrum rigid? Again, that's kind of a lot to write out, so I'm just going to abbreviate it as MLSR. If for all x1 comma g1 and x2 comma g2 in x, you have that if pi1 of x1 is isomorphic to pi1 of x2, and also the marked length spectra are the same. If those conditions hold, implies that x1 g1 and x2 g2 are isometric, then you have a marked length spectrum rigid class of spaces. So this is kind of a weakening of Mostow rigidity, because you have the original assumption from Mostow rigidity, which is that the pi1s are the same. And you have the conclusion for Mostow rigidity, which is that the two spaces are actually isometric. But you have this extra condition here that you're actually requiring the marked length spectrums to be the same. So it's like Mostow rigidity with an extra assumption. And allowing because the fundamental groups are the same, that allows you to kind of compare length assignments to closed geodesics. So this definition is sort of a different version of rigidity that might work in the two cases I pointed out where Mostow does not work.
May I have a question? So why is it called marked? I don't see any marked point here. Marked length spectrum.
Yeah, so the marked length spectrum, so the marked part kind of refers to the fact that you don't just have a list of lengths. So for a length, you know exactly what curve in your surface has that length.
Oh, you mean the location? The location of this length that is achieved.
Yeah, that's right. Yeah, so you know the curve and the length that is assigned to. So there's also something called an unmarked length spectrum. So that's just a list of numbers. So that for that one, you don't know what curve each length corresponds to. So that's what the marked part means. Yeah. And yeah, the marked part is actually pretty important because as it turns out, the marked length spectrum determines the metric on a surface, but actually the unmarked length spectrum does not determine the metric on a surface. So now I think I'm going to give some examples. So the first natural thing to consider is we have this list of instances where Mostow rigidity does not hold. So the first thing we looked at was surfaces. So we can ask, are surfaces marked length spectrum rigid? And I already gave away the answer, but it turns out that they are. So closed surfaces with metrics that are so most natural class of metrics to first consider is hyperbolic metrics. So hyperbolic surfaces are Mark length spectrum rigid. This is actually a fairly old result by Frickett and Klein from 1965. And actually there's something even stronger, which is that you only need to know the lengths of 6G minus 5 closed geodesics in order to determine a hyperbolic metric on a surface. So hyperbolic surfaces are very much Mark length spectrum rigid. And then just like generalizing a bit further, you have, you can have variable negative curvature. So I'm going to star this result because it's pretty well known. So negatively curved, all my metrics are going to be Riemannian. So I'm just going to put that in parentheses, but we're assuming Riemannianness from now on. So surfaces with negatively curved metrics are also Mark length spectrum rigid. So this is independently proven by Croak and Otal in 1990. Again, a really big result. And it kind of inspired a long list of generalizations. So for example, you have non-positively curved surfaces as well. So this is a result by Croak and Fati and Feldman from 1992. So allowing for zero curvature. And then also you have in a different direction, negatively curved still, but with finitely many cone singularities. So this is by Hersonsky and Pollen in 1997. And I can just briefly explain what I mean by cone singularity. So basically these are cone points are points where there's too much angle around them. So the total angle measure around a cone point is greater than 2 pi. And that's just a characteristic of negative curvature. So these are points of too much angle. And yeah, so now we're allowing for some singular metrics as well. And then in sort of along a similar vein, you have singular flat metrics. Again, we only with like finitely many singularities still. So this is actually a result due to a lot of different people. There's like the Duchin, Leininger, Rafi paper where they talk about singular flat metrics induced by quadratic differentials. But the more general result is due to Bonkovic and Leininger. So this is from 2018. Yeah, and then I just wanted to point out the most general result that I know of, which is very similar. So Dave Constantine proved Mark length spectrum rigidity for surfaces with non-positively curved metrics with like finitely many cone singularities. So I think this is the most general result. And this is due to Constantine from 2019. So the short answer to whether surfaces are Mark length spectrum rigid, closed surfaces, this is very important, is yes, there's a bunch of metrics that you can put on them so that they're Mark length spectrum rigid. Yeah, so that's the story for surfaces. And then the next thing on the list of instances where Mostow does not hold is spaces manifolds of negative curvature. So that question is actually still open. So this is a conjecture by Burns and Katak. So it's usually known as the Mark length spectrum rigidity conjecture. from 1985, so it's been open for quite some time. And it says that if X G1, or I can just write it this way, closed, negatively curved, and manifolds for all n are actually Markling spectrum rigid. So this is solved for dimension 2, but for higher dimensions is actually open. So yeah, this is a big conjecture, and there's a lot still to be solved.
May I have a question?
Yeah.
Do you allow punctured surface deleting finite points in
That's a
your?
very good question. No, these are all closed surfaces. So these are all surfaces with no punctures, no boundary components.
Okay. So it must be compact.
Right. Yeah.
Okay.
Yeah. So these are so once she allow for punctures or boundary components, then probably there's no Markling spectrum rigidity result.
Just one question. If it's closed, if it's punctured, but you in this flat singular metric case, that one actually has the same effect as the Teichmiller coordinates. That one, that's a metric ribbon coordinates used in the string theory. That one. So that one, for punctured surface with a singular flat metric, we did have this unique correspondence of the complex moduli to its metric ribbon structure. So that one will give you the isometry.
I don't know if I know of a result like that, but maybe it will work. But yeah, I think all of these results are for surfaces with no punctures or no boundary components. But maybe it could work. I'm not, yeah, but I don't know of any papers. Yeah. Cool. Yeah. So these are just some examples. And now I'm just gonna give some non-manifold examples. So just one other example, and then I'm going to state my result. So another example is compact quotients of Fuchsian buildings, whatever those are, with piecewise hyperbolic metrics. So I just like to mention this result in case you know what a Fuchsian building is, because this was a big inspiration for my project. So this is actually the paper that got me interested in the Markling spectrum rigidity problem in my setting. So I just like to give it a shout out. So this is, I think, a very underappreciated paper by Dave Constantine and John LaFont from 2019. So that's a non-manifold example. Great. So that's kind of a lead into my main theorem. So there's another example of a non-manifold result for Markling spectrum rigidity. So in my case, the two spaces are actually going to be the same. So if xg1 and xg2 are 2, and I'm going to write all of this in quotes and define it in 5 minutes. Simple, thick, negatively curved Riemannian surface amalgams, which again I'll explain very soon what I mean by that, with the same Markling spectrum. So again, in my original definition of Markling spectrum rigidity, I require the fundamental groups to be the same, but now the two spaces are the same, so I don't need that assumption. So if they have the same arc length spectrum, then there exists an isometry. XG1 to XG2 that is isotopic to the identity. So now that my two spaces are the same, I'm allowed to say it makes sense for the isometry to be isotopic to the identity. So yeah, so this is the main result that I'm going to be talking about. And as I promised, I'm going to now define my objects of study, which are surface amalgams. So first I'm going to give a general definition of surface amalgams. It's not very precise, but I think that it gets the job done to give you an idea what these are. So a surface amalgam is constructed by gluing, together finitely many compact surfaces with boundary along their boundary components. So to sort of help you visualize this, I can draw an example. So I'm going to draw a graph of spaces decomposition. So this is, I'm going to draw 3 tori with a boundary component. And all the tori, the boundary components are going to be glued to the same, they're all going to be identified. So if I glue 2 of the tori together, I get a genus 2 surface. And then I can glue a third one on top. So I no longer have an object that's a manifold. So this is a surface amalgam. And it turns out this is a pretty nicely behaved one. So notice that I had all these assumptions up here. I said that there's simple, thick, and negatively curved Riemannian surface amalgams. So I'll just explain what I mean by that. So the first assumption is that my surface amalgam is simple. So this basically means that every gluing curve and this here is a gluing curve. For example, it's just like a curve where a bunch of boundary components are glued together. So each gluing curve is a simple closed geodesic in the surface amalgam. So of course, in order for this construction to make sense, I need to glue by isometries. So like the boundaries, the lengths of the boundaries of all the surfaces of boundary that I'm gluing together have to be the same. And I'm not allowing for higher degree gluings. So yeah, so the name simple basically comes from the fact that these gluing curves are simple closed curves. And also we want all the gluing curves are disjoint. And the reason that I want this condition is because if I restrict to these simple surface amalgams, then I get some really nice properties for my space. For example, I get that my surface amalgam is cat -1. That's a really nice property. I also get that the fundamental group is Gromov hyperbolic. So those are all good properties to have if I restrict to simple surface amalgams. So that's kind of the reason for my restriction. And I'm just going to draw an example where I don't have a simple surface amalgam, but this is like sort of a case that I'm hoping to generalize to in the future. So if I have my surface amalgam from earlier and I glue on an extra torus so that the gluing curves intersect, this is actually a non-example because you have two intersecting gluing curves. Okay. So these are not examples, these are restrictions.
Do you require the glued object to be a manifold?
Oh, sorry, say that again.
The glued object is a manifold, or do you just need a metric space? In the above picture, you glued 3 copies of surface on this boundary. So it looks like, is it still a manifold, the resulted one?
Oh, no longer a manifold. And the reason for that is because you have this singular set. Yeah.
So it could be
So
non-manifold.
right, if you glue 2 of them together, you get a surface, but if you glue that third one on top, then no longer a manifold. Yeah. But they're kind of similar to surfaces. Yeah. And then the second assumption is that you need the surface amalgam to be thick. So this basically means that each gluing curve is attached to at least one other boundary component. So you don't really have these like objects with boundary because as you noticed before, all the Mark-Length spectrum rigidity results were for closed surfaces and closed manifolds. So I really want the object that I'm working with to be boundaryless. So that's the reason for this assumption. So I guess you could replace thick with like boundaryless. Yeah, I'm just borrowing terminology from John LaFont here. And then the third assumption is that it's negatively curved Riemannian. So this assumption is kind of what you might expect it to mean. It means that, so each of these surfaces with boundary, these are all called chambers. So this is kind of borrowing terminology from the theory of buildings. So these are, so for example, for the surface amalgam, these tori are all chambers. So you say that a surface amalgam is negatively curved Riemannian if each chamber is eclipsed with a negatively curved Riemannian metric. So that if you get a piecewise negatively curved Riemannian metric on the surface amalgam. Yeah, so this is, so for example, one thing that you can't have that I'm not considering is you could theoretically glue a cylinder to like a torus, for example. You identify all of the boundary components, you do get a surface amalgam. So this becomes, if you glue the ends of the cylinder together, you get a torus. And then you have another torus of a boundary component attached to that. So this is actually another non-example of a simple thick negatively curved surface amalgam because you can't put a negatively curved metric on your cylinder. So these are just some pictures to give you an idea of the objects, what the objects I'm studying are. Yeah, so this is kind of what I'm studying. And then the third part of my talk, I'm just going to be talking briefly about the sketch of the proof. So
Wait, sorry, I'm a little confused. Why
Yeah.
can't you put an negatively curved metric on the cylinder?
Can you put a negatively curved metric on a cylinder? Because I thought that you can only emit a flat metric.
Well, but if you take, say you take some hyperbolic surface and you look at a simple closed curve in there, and its color is going to be a cylinder.
I guess I always thought that like you can only put flat metrics on chloride, for example, and because like uniformization, I don't know, maybe you can put a negatively curved metric on a cylinder, but I'm not sure how. Yeah, I don't know. Maybe I'll ask about. I don't know if anyone knows the answer to this.
I think the point is that you want the two end circles to have the same length. Otherwise, you cannot, grow as you require. Is that what you have in mind?
You definitely want the two circles to be the same length, but
Yeah, then you cannot have a negative curve.
okay. Yeah, sorry, Michelle. I kind of just assumed you couldn't put one on there. But yeah. But yeah, so next I just wanted to give a brief sketch of Otal's isometry.
Oh, wait, sorry. I just realized that if you do what I said, then the boundary is not going to be geodesic.
Okay, yeah, you do want the boundaries to be geodesic. Yeah. Cool. Right, so Otal's isometry, I just want to briefly describe what it looks like. So you have two surfaces with the same arc length spectrum. And you want to construct an isometry between them. So you can lift a universal cover, which is just going to be a negatively curved disk. And you can take a fundamental polygon for your surface. So for my genus 2 surface, that's just going to be an octagon. And there's a single lift of my original point in that octagon. And I can consider the set of all geodesics that pass through that octagon or pass through that point. So, I'm kind of like missing the point here, but you have a bunch of geodesics in the universal cover that pass through this point x tilde. And then actually there's a quasi-isometry between the universal covers. So this is kind of like some GGT. There's this fundamental theorem of GGT, which implies that there's a quasi-isometry between the universal covers. But the point is that it induces a boundary homeomorphism. So there's a boundary homeomorphism between the boundary circles of the two disks. And that boundary homeomorphism actually determines where endpoints of geodesics get mapped. So if I have this purple geodesic here, I figure out where the boundary homeomorphism sends it. And then there's a unique geodesic between the two endpoints because geodesics are unique. That's like a property of negatively curved spaces. And then the hard part of Otal's proof, the part that requires a lot of work, is that he actually shows that the set of geodesics that intersects at a single point in S tilde G1 tilde, he shows that that set of geodesics actually also has to intersect at a single point in the other copy of the universal cover. So you know that the geodesics have to pairwise intersect, but he actually shows that something like this can't happen, that they actually all have to intersect at a single point. And again, this is what I think is like the hardest part of his proof, and kind of surprising. And this, of course, only works if the two surfaces have the same Mark length spectrum. And then it turns out that you can kind of, this defines a map between the universal covers that's induced by the boundary homeomorphism. But in fact, it turns out that map is pi1 equivariant, so you can project back down to define an isometry. And I just want to point out a main tool here that maybe I'll have time to talk about later. It's geodesic currents. And yeah, so that's Otal's isometry. And then the story for surface amalgams is actually kind of similar, except the universal cover of my surface amalgam is going to be a lot more complicated. So yeah, so I'm just going to illustrate here. I have my surface amalgam that I drew earlier with the same Mark length spectrum. And then if I take two of the tori that lists to a disk once again. So we know what the universal cover of that looks like. And then there's this gluing geodesic that lists to a geodesic in that disk. And then, but then like if I pair up these two tori, that gives me this disk. But if I pair up these two tori, then I actually get another disk. So this one of the half octagons can get paired with another half octagon, so that the two half octagons together tile a plane. And then there's this sort of like branching behavior going on. And then you can lift the gluing geodesic to an infinite collection of geodesics in the universal cover. And there's going to be some half planes branching from all of those geodesics. And then sort of the same thing is happening over on this side, except I'm just going to draw part of it. So yeah, so you can sort of do the same thing. Again, you look at a point X in your surface amalgam and you lift it to some point in your fundamental domain, and then consider all the geodesics that pass through that point. So there's going to be a lot of them because of all this branching going on, but you can still prove that actually all those geodesics get mapped to a set of geodesics that also intersect at the same point in your other copy of the universal cover. And this map is actually pi1 equivariant. So you can project back down. Yeah, so this is how the isometry is constructed. And again, that's just like big picture. I'm not really going into any details here. But Yeah, but the point is that you can construct an isometry like this. And then I just wanted to sort of, I think I have about 9 minutes left. So I'm just going to explain one of the key tools that I use, which is geodesic currents. So I think these are really cool. So I like to talk about them. And they're really useful for marking spectrum rigidity problems. So yeah, and also another fun fact is that Miriam Mirzakhani actually used these to count closed geodesics on surfaces. So that's like another justification I like to give about why you should care about these. But first I'm just going to give a brief definition. So a geodesic current, which I'm going to call mu because it's a measure in the space of currents on X is so for now, X is just a general metric space. So pi1 invariant. So it's going to be a Redan measure. So again, this means that it's locally finite, which means that every point in your space has a neighborhood with finite measure, and also a Borel measure. So it's defined on the sigma algebra generated by open sets. So it's this pi1 invariant Redan measure on the set of unoriented, unparametrized geodesics in not X itself, but the universal cover of X, actually. So I guess in a nutshell, it's like a nice measure that you can put on geodesics in the universal cover. And yeah, and there's some really nice examples of geodesic currents that are really useful. So one example is something called a counting current. So this is associated with an element of pi1 of X. So if you have a measurable subset of your space of geodesics, which I'm going to call script G of X tilde. So this is sort of my measure space. Yeah, the measurable subset of this, the unoriented, unparameterized geodesics, you can define the measure of that subset as just like the number of times that subset intersects like all the lists of alpha in the universal cover. So this is the full pre-image of alpha under the covering map. So again, take all the lists of alpha and just count the number of times your E intersects alpha. And so you can see that this could be an infinite measure, but that's okay because as long as it's locally finite, it's a geodesic current. So this is a really handy example of a geodesic current because these are actually dense and you can topologize the space of currents, and these are actually, or linear combinations of these are dense in the space of currents. So that's really convenient. But the other current I wanted to focus on is called the Liouville current. So yeah, so I'm actually not going to define this one because the definition is a bit more involved. But I'm going to point out a useful characteristic, which is that if you have if I is a geodesic, either a closed geodesic or a geodesic segment in X, and I tilde is a single lift in the universal cover. What you can do is you can consider the space of geodesics that are transverse. So that's actually not a well-defined notion, but it is kind of what you expect it to be. So these are geodesics transverse to I tilde. So for surfaces, for example, I'm just gonna quickly draw a picture here. If I have a closed geodesic, I can take some lift of it in the universal cover, which is a disk. So that's I and that's I tilde. And then I look at all the geodesics that are transverse to it. So those are all in script G of I tilde.
So do you allow the geodesic on X to be closed or maybe generic, so that could be done everyone does on the manifold? Which kind of geodesics are you considering? It must be closed or some.
Do you mean the geodesics and script G of I tilde, or do you mean
On X, yeah, on X, could it be very complicated one? On X,
yeah. So these geodesics are just like any geodesics on a universal cover. They don't have to project any closed geodesics in your surface.
Okay, so even on the flat torus case, you may have some irrational slope type of geodesic that is.
Yeah, so I'm only considering negatively curved objects in this talk. So I'm not looking at torus tori, for example, but yeah, in theory, like any geodesic that you see in the universal cover can be included in this measurable subset.
So don't require them to be closed. Don't require
Right.
them.
Yeah.
Okay.
Yeah. So there's like this really cool relationship between the length of I and the Liouville current. So the measure of this set is actually equal to the length of I in your surface. So there's like this relationship between the length, the marked length spectrum, and the Liouville current. Sorry, this is a capital L. So this here is a G length of I in your surface. And then you have something really similar for surface amalgams, which I'm going to abbreviate here. So almost all of them have the same property. If I is not included in a gluing curve, you just get the length of I. But if I is included in a gluing curve, then there's actually that extra multiplicative constant. So if I is contained in a gluing curve attached to n boundary components. Yeah, so you can sort of do a sanity check here. A closed surface you can think of as a surface amalgam where every gluing curve is attached to exactly 2 boundary components. So n would equal 2 in that case. So then you have 2 over 2, which is just the length of your gluing geodesic. Yeah, so this is like a really convenient relationship between the marked length spectrum and the Liouville current. And the Liouville current is really instrumental in my proof of marked length spectrum rigidity. Yeah, so I think that I'm out of time, so I'm just going to end there. But feel free to ask me any follow-up questions.
You have some continuity dependence on the marked length spectrum. So suppose two manifolds have very close marked length spectrum. Does that mean they are almost isometric, very close to each other?
Yeah, there's some work by Karen Butt. So she studies I think she's at Chicago now. She studies approximate marked length spectrum rigidity, and that's sort of like the idea that you were talking about. Yeah, so yeah, she has some papers about that.
So I think that maybe you mentioned when you were giving the defining what you meant by these surface amalgams, that like if these restrictions are satisfied, then your group is Gromov hyperbolic. Did you say that? Okay.
The simple restriction. Yeah.
Okay.
Yeah.
So I still want to understand the name marked because each geodesic which achieve this minimum has a number, so have a bunch of numbers. And so when you say the marked, what's the exact meaning? The marked means there are location on the manifold or some topological relation between these geodesics, or what's the meaning of the marked?
Yeah, marks just means that if you have a length in your spectrum, you know what curve it's associated to. So yeah, so you have like an actual length assignment. You don't just have a list of numbers of lengths of curves.
Yeah, I just feel your conclusion is you can show eventually with the same marked length spectrum, you imply two manifold are isometric. But this is because when you say marked, already you have some information of the manifold already. So so it looks like some kind of cyclic conditions. In order to talk about the marked, you have to identify the manifold in some way to talk about they are marked in the same position. But your conclusion is these two manifolds are isometric. So this condition and the results, they have somehow have some overlapping.
I don't think I really understand the question, but
well, how can you say these two things are yeah. Can you show me one example that marked non-spectrum is different from the non-spectrum? So just want to understand the meaning of the marked.
So yeah, if you remove the mark and you just look at the set of lengths,
Yeah.
Then it's no longer rigid. So you can construct pretty easily examples of actual hyperbolic closed surfaces with the same length spectrum that are not isometric. But the problem is that sometimes some of the lengths that in one surface corresponds to a simple closed curve, and the other one it can correspond to a non-simple curve. So the marking sort of gives you, like, it prevents that from happening.
You mean multiplicity? So marking in this case is the multiplicity.
But not just multiplicity. I mean, just like a non-simple curve, like some sort of self-intersection. Things like that can go wrong. Yeah, so I think the point of the marking is that, like if you, so I'm thinking just of a hyperbolic surface. If you have some sort of topological surface with representatives for each conjugacy class in the fundamental group, then you have this, the marking is like this map that goes from the fundamental group to the set of lengths, and so it's not just an abstract set.
So they carry some topological information in the,
yeah,
they mirror, they have some homomorphism inside this fundamental group, and that gives some kind of configuration of this connection of geodesics. That's the meaning of the marked.
yeah, yeah, if you're curious about what Michelle is talking about, there's a sonata construction. So he shows that there's a lot of examples of hyperbolic surfaces where the unmarked length spectrum, so just a list of numbers, is not enough to determine the metric.
Yeah, on one hand, by this function Nielsen coordinate of the hyperbolic metric, because you may have different topological types of this complex moduli. So even you have the same collection of numbers, but because of this different combinatorial types, they represent the different conformal moduli. So is that roughly the meaning of marked? You don't simply give this function Nielsen coordinates, these numbers, but you also have some combinatorial relations, some topological. I think the dual picture is a metric ribbon diagram that one has this function Nielsen coordinate translated to the length of this interior edge of this metric ribbon diagram, and this metric ribbon graph topological structure is that one roughly correspond to your meaning of marking. So it's not just numbers, but the numbers are put on certain graphs.
Probably, to be honest, I'm not sure what half of the things you just mentioned are, but yeah, I think that maybe you have a different way of thinking about these than I do, but I just think the unmarked length spectrum is a list of numbers. The marked length spectrum is, you actually know what curves those numbers correspond to, and that's the difference.
Thank you.
Yeah.
So still, yeah, I want to ask one particular case you mentioned in the beginning. So there is a case called flat singular metric on the Riemann surface. So